Hello and welcome back. Today we're going to be creating our AI nav pathfinding, and this is going to be the code that will be generating the path for the AI to actually crawl on the ceilings and stuff. That being said, this is going to be a very large subject, so we're going to be splitting it into two parts. The first part is going to be going over how to create a path that will move along the ground, jump up onto the wall or the ceiling, and then move along the wall or ceiling and have the chance of jumping back down and have all of that be very fluid and just work with the AI as it currently stands. It's also going to be having code to handle the grounded state, as we need a enum to determine whether it's on the ground, in the air, or on a wall or ceiling. Then we're also going to be working on some error handling to make sure that if the AI happens to get closer to the next waypoint due to physics or what have you, as this is a physics-based AI movement, then it will go ahead and just jump to the next waypoint instead of trying to get to the current waypoint. And then we're also going to be doing a check to see if we have been trying to get to a waypoint for too long, we need to go ahead and generate a new path to try and get to the target location to make sure that the AI doesn't get stuck too much. We're going to go ahead and dive into a Blackboard real quick before we get to the code, and we'll use that to kind of break down what the current objectives are and how we're going to be achieving them. All right, we're in the Blackboard here. This is kind of where I originally started. My intention was to create a 3D model that would represent all of the navigatable areas, much like an auto-generated nav mesh that would be on the floor, but this would actually wrap around the surface all the way up to the ceiling and all the pillars and everything. This would allow navigation anywhere on any of the surfaces in the game. And the way this works is you take a point A and a point B, that's the origin point and the target point, and the nav mesh will find the two closest points on the mesh and then navigate through the mesh in order to find the closest distance. And it does this through some wizardry on the back end that I'm not too concerned about. Then it creates a series of waypoints which are marked in green here. Now this does work, but the problem wasn't actually with the nav mesh. I ended up running into the problem when it came to authoring the nav mesh. So this is kind of what I actually got to, and what it amounts to is a sculpted out 3D model that is then shrink wrapped to the scene geometry to create a nav mesh. And this was very slow to create, and I realized about halfway through, when I got about this much done, that this was going to be pretty much impossible for me to recommend anyone to actually make besides myself. And since I couldn't recommend it to anyone else to make, I figured implementing it into the project really wouldn't be viable. So what I decided to do was something a little bit different. So first off, we have our level geometry, and that's in white here. Then we have the auto-generated nav mesh, and that's in blue here. And say you want to get from point A to point B. The automated nav mesh, just like up there, will go ahead and create you a path, which is a series of waypoints from point A to point B. Now these waypoints are highlighted in green. So my basic idea was, using this path, I can typically decide that there will be geometry somewhere in the ballpark of this path. So every so often, say about 10% of the time, we'll go ahead and decide that we want to be on the ceiling or on the wall or what have you. So from one of these points, say we decided this right here. We'll go ahead and create a raycast, which will pick a random direction upwards. Let's say it goes over to the right. And using that, it will go ahead and find the location on the wall that counts for this. This will create a jump target. Now, what this will do is when the AI is coming along, instead of continuing on to this node, it will now jump towards this node and attach to the wall. And then because of this raycast being successful and us knowing that there is a wall up and to the right of this, we'll go ahead and reuse this same ray further on for every node as we progress. Now, there may come a time when that node will be incorrect or simply too far away from the wall, at which point we will decide we now need to go ahead and move back down to the ground. And at this point, the AI will go ahead and jump down. This creates a new path that allows the AI to run, jump up onto the wall, run along the wall, and then jump back down. Now, in practice, this actually looks pretty good. The movements are fairly organic, and this allows the AI to pretty much interact with any environment. The only downsides being that it really doesn't work well with extremely tall rooms. So if you have a room like the entrance up here, the AI aren't really going to run all the way up the entrance, because generally they're trying to get from their location to your location, and that doesn't really necessitate going up the entrance further. Now, there are a couple issues with this. Say, for example, you have a second path that instead of going in between the pillar and the wall, goes outside the pillar. And say you're already running up the wall, which means that these rays are cast every so often, and the AI's current position is actually on the wall, running along. Now, this ray right here would actually impact the pillar, and thus the AI would believe that it should run along the wall and then run all the way over here, and then run all the way back to the next point. And obviously this is incorrect. This is impossible. So there's a couple safeguards that I ended up taking to resolve this. First off, anytime it is raycasting along like this, if the raycast point is more than about 25% greater or less than the original raycast point, then it will go ahead and just break out and go back to the walking position. This will allow the AI to kind of handle any pillar. It just kind of snaps out of running on the wall when there's a pillar between it and its original path. Now, this does result in them coming off the walls fairly frequently if there's a lot of pillars in the environment, but it also doesn't look half bad, so it gets the job done. Now, besides that, we also have a slight issue with overshot. So due to the way we're actually jumping up onto the wall, it's very conceivable that we may end up actually farther down the path than we had originally intended. So I do a little bit of math to resolve this. If the AI's actual position is closer to the next waypoint than it was to the previous waypoint, we just go ahead and erase the previous waypoint and go on to the next waypoint. And that's pretty much it. The end result is now we can have AI run along the ceiling, run along the walls, and jump back down and interact with each other in a fairly fluid and natural way. Now, that being said, the path generation and the actual navigation of the path we're going to be breaking up into 2 separate videos, as they are fairly complex subjects, and I don't really think I could get a single video with all of it without it being excessively long. So we'll have this video this week, and then next week we'll actually go over how to make the AI move along it. That being said, let's go ahead and dive in and get started. Alright, so hopefully you have a fairly solid idea of what we're going to be doing now. So we're going to be diving right in. The rollerball right here is what we need to modify. And we can do a couple things before we dive into code. So we can go ahead and delete the navigation agent 3D as we won't be needing it anymore. We'll be doing everything inside of the rollerball code. And that's the basic enemy navigation agent here. So we can go ahead and select this and open up the code. So first off, let's start with a couple exports. We can go ahead and just comment out we can go ahead and just delete the navigation agent, and let's put this inside of a path navigation group. In addition to this, we're going to put in a minimum launch delay. This is just going to be a delay to make sure that we don't launch a whole bunch of times rapidly. And the launches are defined as the time when it needs to transfer from the floor to the ceiling, or from the ceiling to the floor, or whatever wall you happen to be on. And by putting in a little bit of a delay here, we make sure that we don't overdo it. We don't launch multiple times in like the space of half a second or something, as the launches are going to be a pretty strong jolt to the physics. And it may take a frame for that to actually be registered, and we don't want to have multiple jolts that will end up launching the AI all over around the place like a ping pong ball or something. Speaking of which, we can go ahead and create a signal for the launch request event handler. This will just be fired off whenever we do actually want to launch, and that will be listened to by the limb controller later on to actually tell the limbs what to do when a launch is requested. Now, in addition to this, we can go ahead and create a new group, and the first group is for the navigation of the agent. The second group is for actually generating those paths to navigate down. And right out the gate, we're going to go ahead and create a Boolean for debug active. This is going to be invaluable later on for determining where the path is actually being generated at. Following that, we can go ahead and do a grounded check distance. Much like with most AI, you need a check to see if we're on the ground, but this is going to be a little bit different, and I'll explain it later on when we get into that code. Following that, we're going to have a stopping distance, and this is exactly like with the navigation agent 3D. It's just going to be the distance at which we kind of register that we are at a given waypoint. Following that, we'll have the wall roof distance change allowance. The up path check distance is going to be the distance that it actually checks upwards at random angles to see if there's a wall. And this is kind of our limit for how far we're willing to jump up onto a wall. So make sure you don't set this to too high of a number. Speaking of which, we're going to need a world collision. This is going to be of type uint, and it's going to be a property hint layers 3D physics. This is just going to be a collision matrix for determining what it's allowed to crawl on. And now we have the chance of up path. All right, I actually stated this one wrong. So the wall roof distance change allowance is the amount of change forward and backwards in distance that the AI will consider a break in the wall. So about 25% I found was good, because that means that it can't get 25% farther away or far more than 25% closer. And as a result, that just means that it'll generally run across a wall, but if there's like a pillar or something in between it and the wall, it'll go ahead and hop off the wall and go back to the ground. And then the chance of up path is what I actually was saying that this one was earlier. I just mixed those up. And yeah, we typically set that to about 10%. Now we have our desired velocity here, and we're also going to go ahead and add a target position. This is just going to be wherever the AI is currently moving towards. And just below that, we're going to have a object of type path waypoint, and that's going to be the last retrieved path waypoint. Now we do need to go ahead and create a new class that's going to be used for the waypoint system. And that's just going to have a couple things that'll be needed for actually navigating the world. So we'll have a waypoint position, a waypoint normal, and that's going to be like the surface that they're walking along. And then a Boolean saying whether it's not the floor. So basically, if the AI does want to run on the wall or something, this will be true. We can use that as reference in the AI controller later on. We also have a waypoint estimated duration. The estimated waypoint duration is kind of there to make sure that the AI doesn't stand around trying to get to a waypoint for too long that it can't reasonably get to. And basically, if time elapses while it's trying to go to a waypoint more than this duration, then it will go ahead and reset the path and just generate a new path to its current target position. And this kind of helps it keep it from getting stuck. Now, just below that, we're going to create a new enum. It's going to be called grounded state. As we are going to be on the wall and sometimes in the air, we need a grounded state that kind of reflects that. Instead of just a Boolean saying we're grounded or not, we're going to have a enum that says whether we're in the air, on the floor, or on a wall or roof. And we can go ahead and have a current grounded state. This will just be accessed from the AI controller later on in order to see where the AI currently is. We're also going to have a current ground normal, and this is going to be used once again in the AI controller to determine which way it should rotate. And that's not necessarily going to be the actual path waypoint normal, because there's sometimes a little bit of inconsistencies between the two. It's based off of where the AI actually currently is, because when we retrieve the grounded state, we can actually pull the normal at that time. So we're going to go ahead and have a current ground normal variable. Now we're into private variables. We're going to go ahead and create a initial wall roof distance, and it's going to be equal to 0. This is going to be used to determine what the distance in the wall roof distance change allowance is, because whenever we start walking on a wall, we'll set this, and then anytime it gets too far away based off of that, we're going to snap out of walking on the wall. We're also going to have a float for the launch attempt interval, and this is just going to be a temporary float that's going to be used with the minimum launch delay to ensure that we don't launch too many times. A waypoint failure timer, and this is going to be used with that estimated waypoint duration to make sure that we don't stand still for too long. Then we're also going to have an internal gravity scale. This is going to be used to determine what the gravity is supposed to be. As with the rollerball, I actually set it to slightly different than normal gravity. We have a gravity scale of 1.12. I found that that looked the best. By setting the internal gravity scale to that at startup, we can use that as reference when we swap on and off gravity. As when we're on the ceiling, we're actually going to be turning off gravity so that the AI can actually be stuck to the ceiling. And then we're going to add a little bit of a push constantly towards the wall. Just below that, we're going to go ahead and create a random number generator that's just going to be used in the AI path. And by caching it here, it just means we don't generate a bunch of extra memory for no reason. And then we're finally going to have our proper current path. The current path is going to be a list of path waypoints, and it's just going to remove the bottom one each time it reaches a waypoint, and then the next waypoint in line will be whichever waypoint it needs to head towards. We're going to have something called a RID, and an RID is kind of like an ID to point towards a object in memory. And in this case, it's going to be pointed towards the nav mesh, which will be used to generate the paths. By caching it right here, we don't run costly measures trying to determine what the nav mesh is. Though that being said, if for some reason this AI did need to navigate to another scene or something like that, or a new nav mesh was added, you might need to re-update this. And we can finally get into our ready function. So first off, we can go ahead and assign that nav map to the getWorld3D.navigationMap. Now getWorld3D is just a function that's in all node 3Ds. And it's going to go ahead and return kind of information about the world that the node is in. And then we're just going to use that to get the navigation map that is currently in that world. We're also going to go ahead and set our internal gravity scale equal to the gravity scale on the rigid body. And then we're going to go ahead and randomize our RNG. And we're going to go ahead and get a float between 0 and the minimum launch delay for the launch attempt interval. This just ensures that when the AI first start out, they don't all jump at the exact same interval, and this kind of gets them an initial start value. We're going to go ahead and erase that physics process, and we're going to create a couple functions first off. We're going to create a new function called setNewTarget, and it's going to be taking a vector3 and it's going to be generating our current path. So let's first off clear the current path. Next, we'll randomize our random number generator and create a new path using the navigation server 3D.mapGetPath and pass in the navmap RID, which will just tell it what nav mesh to be using, as well as our global position, our new target, and then we also have a Boolean for optimize, and we're just going to pass it false for the optimize. This means we'll get a fair number of waypoints, but this also means that our movements will be slightly more organic, and I'm not really concerned about optimization at the moment, though you may want to set this to true. And that returns an array of vector 3s, which we can go ahead and iterate through and add back to our current path. But first off, we're going to create a couple variables. We're going to create a vector 3 for our current up vector, which we're just going to default to vector3.up. Our last waypoint is going to be our global position. Each time we step forward in the waypoints, this one's going to be the previous one, and we're going to use it to determine the estimated waypoint duration. And then we're also going to have a last on ceiling, which is just going to be used in order to determine if we were last on the ceiling, we want to default to being on the ceiling and use that same vector, the current up vector, as our reference for the direction we're currently walking on that ceiling. Then we also have our current path chance. Now our current path chance is the chance of up path divided by our new path dot length. And this is just going to make sure that the up path, which is currently set to about 10% at the time, is 10% of all paths, not 10% of all waypoints. Otherwise you end up with way too much noise in the random chance there. Now, real quick, we have our last retrieved waypoint here, and we can go ahead and use that. If the last retrieved waypoint does not equal null, then we'll use its last on ceiling. This way, in between repath events, we are consistent whether we're on the ceiling or not on the ceiling. So if we jump up on the ceiling and then halfway across the room we repath, it will start out on the ceiling, and it may fall off afterwards, but at least it'll be fairly consistent right out the gate. And for each waypoint in the new path, we're going to go ahead and do a function here. Now, first off in the function, we can go ahead and get our estimated duration. This is just going to be the last waypoint, which starts out as our global position, but is whatever the waypoint previous to this one is. It's distance to the waypoint divided by our maximum velocity. And this is kind of always going to be an overestimate, but it just works out fairly well. Then we're going to check to see if we were last on the ceiling and a random number between 0 and 1 is less than our current path chance times 2. This means that we were last on the ceiling, but we do want to go ahead and randomly decide to jump off of the ceiling. We're going to set our last on ceiling to false. And this is just going to handle climbing on the ceiling, but then deciding to jump off. Then right after that, we're going to go ahead and set our last waypoint equal to waypoint. And the reason why we do it after this function is I like to go ahead and put in a debug function here. So we're going to say if debug is active and we decided to jump off the ceiling, then let's go ahead and create a new line between the last waypoint, the current waypoint, and we'll set this to the color blue and leave it for 2 seconds. This just means that whenever we're jumping off the ceiling, we go ahead and have that debug marker. Next up, if we aren't currently on the ceiling, let's go ahead and decide whether we're going to go up onto the ceiling. And if the random number between 0 and 1 is less than the current path chance, then we'll go ahead and create a new up vector and continue. And if it's not, we're just going to add the waypoint as it currently stands on the nav mesh on the ground. And for that, we're just going to have the waypoint normal be vector3.up. We're also going to have the waypoint position equal to the waypoint we're currently iterating over. And we're just going to say it is on the floor. So waypoint not on floor equals false, and estimated waypoint duration equals estimated duration. Then we're going to use the continue, and the continue keyword will just go to the next waypoint. But if we have decided to be on the ceiling, then we have created a current up vector, which is just vector3.1 plus vector3.1 multiplied by a random variable. This just gets you a random vector that generally points upwards. And since we aren't using the continue keyword, it'll just move on down to line 112 down here. Now that we've got an up vector and we are wanting to be on the ceiling, we'll go ahead and use the getWorld.directSpaceState, and we'll create a new raycast parameters using the physics ray query parameters 3d.create function. We're going to go ahead and pass in it a from and to, which is just going to be the waypoint, and then the waypoint plus the current up vector normalized multiplied by the up vector check distance, and we're going to pass in that world collision matrix that we had before. And we get the result by just saying spacestate.intersect ray. And it just occurred to me, I can go ahead and put this space state down here. I don't have to have it inside the for each loop. That'll save a little bit of performance. In order to see if we have intersected with the world, we just go ahead and check to see if the result.count is greater than 0. And result is just a dictionary of whatever the variables are, which you can see right here is the position, normal, collider, so on and so forth. So if the result is greater than 0, then we're going to go ahead and create a new path waypoint, which we will be adding into current path in just a second, but we need to do a couple things to it first. So first off, for the waypoint normal, we'll go ahead and get the result normal, and you can just use the little square brackets there in order to fetch the normal, and we can cast that to a vector3. We also set the waypoint position equal to the position of the result, cast to vector3. And finally, for the waypoint not floor, we do equal it to true because we are now on the ceiling or the wall, and we set our estimated waypoint duration. Now, there's a couple things that we want to do before we actually pass that over to the current path. First off, we're going to get our current distance, which is going to be the new waypoint's distance to the origin waypoint. So that's the waypoint in the new path that we're currently iterating over. The new waypoint is the actual point up on the ceiling. So we're going to get the distance between its position and the original waypoint that we started at. Next up, we go ahead and get our current change delta. Now, the current change delta is going to be used with the wall roof distance change allowance. And by taking the current distance, so say we're 10 meters away from the waypoint, and the initial wall roof distance, say that's 15 meters away from the original point, we subtract that from the original and you get -5. You divide that by the initial wall roof distance, so -5 divided by 15 would be -0.03. And then you get the absolute value of that, and you can compare that to the wall roof distance change allowance to determine if it has changed too much. So -0.3 would have changed too much, because if it's the absolute value, it'll be +0.3, which is greater than that allowed change. So we can just go ahead and check to see if we are currently on the ceiling and our current change delta is greater than the wall roof distance change delta allowed. We can go ahead and set last on ceiling equal default. So this will go ahead and break us off of that ceiling. However, if we're not on the ceiling, or the current change delta is greater than the change allowance, then we're going to be going onto the ceiling if we're not already. So let's go ahead and check to see if we aren't currently on the ceiling, then we need to go ahead and set the on the ceiling to equal true. And we're going to also go ahead and set that initial wall roof distance. That'll be whatever the basis for all of the other ones is. Now, something to be aware of, if you are coming through this the first time, then that current change delta, the initial wall roof distance is just going to be 0. So dividing by 0, you're just going to get 0. So whatever the current change delta is will not be greater than the wall roof distance change allowance ever. So by default, the first time it comes through, it will come out as true. So we'll be going ahead and jumping on the ceiling because the random range right here was less than the current path chance. All right, and then we're just going to go ahead and add that to the current path, and we're going to continue. Now, if the results.count is greater than 0, then we did impact the wall. We're going to go ahead and do that. However, if we haven't, then we have not impacted the wall, and we need to just go ahead and continue on about our day. And if we have not impacted the wall, then we're also going to be not on the ceiling, so we're just going to say last on ceiling equals false. And that'll be pretty much it for there. Now, that's all of our for each loops, so that creates our path as we need it. Now, next up, we do need to do a couple things. So if our current path count is greater than 0, then we do need to go ahead and set our current target position to the current path count -1's dot waypoint position. That's just going to be whatever the last waypoint in the current path is. And if that's not true, we're just going to go ahead and set it to the global position. That way, if the path for whatever reason is just too close to the AI, or there's some sort of issue with the pathing, it'll just come out as being the target position is the global position of the AI. And last but not least, we're going to go ahead and check to see if the debug is active, then we're going to set a variable of the last position to the current global position, and we're going to iterate through all of the waypoints, building debug lines between each of them with the color red as the debug line, with a value of 5 seconds for each line. Then we're just going to set our last position equal to the waypoint.waypoint position as we loop through, so that way it just kind of loops through all of the waypoint positions, drawing a line between each one. That's just going to be used for reference. And that's going to do it for creating our path. Now we need to go ahead and create a function for checking to see if we have reached a waypoint. So let's go ahead and create that. This is going to be just private void waypoint reach check. And first off, we're just going to check to see if the current count is greater than 0. And if it's not, we're just going to ignore it. Current delta is going to be our waypoint position minus our global position. So that's just going to be the direction we should be moving in. And we're going to create a Boolean here for just checking to see if we're closer to the next waypoint than we are to the current waypoint. And for that, we're going to check to see if the current path count is greater than 1. That means there is another waypoint to go to. And if so, we're just going to check to see if the current closer to next. And for the closer to next Boolean, we're just going to assign it whether the current waypoint position's distance to the global position of the AI is greater than the next waypoint's position's distance to the global position. And so basically the Boolean will be true if we happen to be farther away from the current waypoint as we are from the next waypoint. And we're just going to check to see if the current delta's length is less than or equal to stopping distance. That means we're closer to it than the stopping distance, or we're closer to the next one than we are to this one. Then we're going to go ahead and create a Boolean, and this Boolean is going to be called launch. It's just going to be used to determine whether we need to call that signal saying that we need to launch requested. And this is going to be true if we are currently on a waypoint that is not on the floor or is on the floor, and the other waypoint that we're going to is the opposite. So it's either we're on the floor and we're going to a place that's not on the floor, or we're not on the floor and we're going to a place that is on the. Either way, we're going to need a launch event to occur. And within this, we can go ahead and set our current path remove at 0. So that's going to remove the bottom one in the path. And if launch equals true, we're just going to go ahead and set our interval to the minimum launch delay, and we're going to emit the signal for the launch request. Now, the reason why this launch attempt interval is going to be here is every so often, if we're still not on the floor and we should be on the floor, or we're still not on the ceiling and we should be on the ceiling, we're just going to go ahead and fire off another launch event every so often to try and get us back to where we're supposed to be. Now, following this, we can go ahead and create a couple more helper functions. We can create a function that just says if our target is reached or not, and that's just going to be a boolean to returning whether our current path count is equal to 0. So basically, if there's no more positions in the path, then we have reached our target. Then we're also going to have a function for get final waypoint, and that's just going to be checking to see if our current paths count is greater than 0, then we go ahead and get the last one. But if not, we're going to go ahead and call a function called get next waypoint. Now, the reason why we do this is because get next waypoint is going to have a little bit of logic in it to handle if there are no more waypoints remaining to get the last sent. So let's go ahead and create that function. We'll put it right down below get final waypoint. So get next waypoint. In here, we're going to do a couple things. So first off, we're going to check to see if our current path.count is greater than 0. And if so, we're going to check to see if the last retrieved path waypoint does not equal the current path's first element. And if that does happen to be true, we're going to go ahead and set it to equal the current path's first element. And we're going to set our waypoint failure timer to the estimated waypoint duration. This is just going to make sure that whenever we do update our path, we go ahead and reset that waypoint failure timer so that it can go ahead and iterate down. And if it reaches 0, then we're going to go ahead and repath anyways. Then we go ahead and return the last retrieved path waypoint. Now, just below that, if we don't currently have a path and we're trying to get the next waypoint and the last retrieved path waypoint equals null, then we're going to go ahead and create a new path waypoint with a normal of just up with our waypoint position equal global position and waypoint not floor equal to false. Reason for this being is we just want to go ahead and make sure that even if there is nothing, if there's never been a path before and we're getting the next waypoint, we go ahead and generate something to return. And then we're just going to return the last retrieved waypoint path. We can actually break that out below. Let's go ahead and remove those from there. And whatever happens, we'll return the waypoint path. This means that whenever we get the final waypoint, if there is no path at all, then we're just going to return pretty much the default to ensure that something gets returned every single time. I don't want any null reference exceptions here. Now, there's a couple more functions that we need to do before we actually get into the process function, which will kind of iterate through all of this. The first function is going to be get the ground normal, and that's just going to be get current ground normal right here. And that's going to be generated when we use the grounding function. So the next one is get current normal. Now, current normal is the normal of the waypoint. It's not necessarily the normal of the ground we're currently standing on. This can be useful later on for other things in the AI controller, so we have these differentiated. Now, the final function before we actually get back to the physics function is going to be the get grounded function. Now, our grounded function in a normal state would just be cast array cast down and see if we're on the ground. But for this, we're going to need something a little bit more complicated, as it returns grounded state which has none floor or wall and roof. So first off, let's check to see if we're just in the air. For that, we're going to be doing something called an intersect sphere. So it's just going to be an overlap sphere, essentially, if you're from Unity. For this, we're going to go ahead and create a new query, which is going to be physics shape query parameters 3D. Then we're going to set its shape to a sphere shape 3D with the radius of ground check distance. We're going to set its transform to our global transform, and we're going to set its collision matrix to the world collision matrix. We can go ahead and get our space state, and on that space state, we can go ahead and call the intersect shape function, and we're going to go ahead and pass it the shapes query. So first off, we're going to check to see if the count is greater than 0. That means we are near something. The sphere cast did intersect something, and if that's not the case, then we're just going to return grounded state.none. That means we are currently in the air. We don't need to worry about anything else, and the current ground normal equals vector3.up. So that's kind of the default for the current ground normal. Now, if we are near something, if the results count is greater than 0, we can go ahead and set the current normal to get current normal. That's going to be whatever the waypoint we're currently standing on, or whatever waypoint we should be going to is normal. And if the current normal is vector3.up, then we know that our waypoint we're currently going to is supposed to be on the floor. So we're just going to default to the grounded state.floor. This is going to ensure that even if we're on the wall or something, if we're supposed to be on the floor, just run normal gravity on it. But if that's not the case, then the waypoint we're supposed to be going to is on the wall because its normal is not vector3.up. We need to go ahead and check a raycast against that. So let's go ahead and create a new query for the physics ray query parameters 3d.create function, just like we did down here in the path generation. And we're going to set its start position as our global position and its destination equal to our global position minus the current normal multiplied by the grounded check distance. And this is just going to be the direction that we're supposed to be against. So if we're on the wall, the normal is going to be pointed away from the wall. And so by subtracting from it, we just go ahead and get the opposite of that. So we're going to be pointed towards the wall, and we're going to be passing it the world collision. Then we're going to be using the intersect ray function to go ahead and get our raycast results. If our raycast results is greater than 0, that means we are near the wall or the ceiling, which means we need to return grounded state.wall or roof. And before we do, we need to go ahead and set our current ground normal to whatever the normal of the raycast we just raycasted against. That way, when we're walking on the wall or what have you, we can go ahead and check against the normal of the terrain that we're actually walking on to rotate the upper torso to actually kind of like stick to the wall or the ceiling. And if this is not the case, then that means that the shape query for the sphere says that we are near something, but the raycast that we cast did not find anything, which means that we are standing on something, but not in the direction of the wall. So that means that we're going to be standing on the floor. So we'll just go ahead and return grounded state.floor. And that's pretty much the entirety of the get grounded function. Now we can go ahead and hop up to the physics process function. And we'll go ahead and create a public override void for physics process. Now this is where the real meat of the navigation agent is. So first off, we're going to go ahead and check to see if we have reached our next waypoint. We're also going to set our current grounded state to the get grounded function. This is just going to be kind of our general maintenance of the pathfinding. That's going to be running all the time. And then we're going to check to see if our target is currently reached. We need to set our desired velocity equal to vector 3.0 and go ahead and return. And this is going to stop out anything else from processing. However, if we haven't reached our current target, that means we do have a path we're traveling down and we do still have waypoints in it. Then we need to go ahead and do the logic for the pathfinding. So first off, let's go ahead and subtract from our current waypoint failure timer. And if that's less than or equal to 0, we need to go ahead and create a new path, so that we'll use just the set new target function with the target position. So that's wherever we were already pathing towards, but we're just going to generate a new path. Following that, we're going to go ahead and create a new waypoint path. We're just going to call the current waypoint, and we're going to equal it to get next waypoint. And if the current grounded state equals to none, we're just going to set the launch attempted interval equal to the minimum launch delay. So this way, we're just going to keep updating that. And then whenever we actually land, we can go ahead and subtract from that. So that way, if you're in the air, it resets the launch attempt interval so that you don't jump immediately upon landing on the ground. However, if we're not currently in the air and our launch attempt interval is greater than 0, we're just going to subtract from it delta. This is going to be used later on, but not just yet. So we're just going to leave that there. So following this, we're going to go ahead and check to see if our current waypoint's not on the floor. So that means that we are wanting to walk on the roof or the wall. We're going to check to see if our grounded state equals wall or roof. That means we are currently on the wall or roof. We're just going to go ahead and subtract from our linear velocity the current ground normal multiplied by 0.5. I found this was a pretty solid number to just kind of stick the AI to the wall a little bit. It doesn't really stop them from moving around or jumping off the wall or what have you, or even if you shoot them, it'll knock them off the wall easy enough. But it does mean that they tend to just adhere to the wall, and it results in a pretty good visual. Then we're going to go ahead and set our gravity scale equal to 0. If this is not the case, that means we're in the air or on the floor, but our waypoint says that we want to be on the wall. Then first off, we're going to go ahead and set our gravity scale equal to the internal gravity scale, because we do need to be falling if we're in the air or on the floor. And then we're going to go ahead and check to see if our current grounded state equals floor. So that means that we are wanting to be on the wall, but we are currently on the floor. Then we're going to go ahead and check to see if our launch attempt interval is less than or equal to 0. That's that interval that we've been subtracting over here. And then if that is the case, we're going to go ahead and reset it, and we're going to emit the signal for launch requested. This just means that anytime we're wanting to get onto the wall, but we've been on the floor for a little while, it will go ahead and emit that signal. So that means that the AI will jump, land, and if it didn't actually land on the wall, it'll kind of wait around for about a quarter of a second, and then it'll jump again. So that way we've got a nice little interval. We've got a cycle to keep it attempting to get on the wall. Now remember, because of the waypoint failure timer, if it attempts this too much, it will eventually generate a new path. Now, if our waypoint is not on the wall or the ceiling, it is actually on the floor, we don't have to worry about any of this. We can just set the gravity scale equal to the internal gravity scale. So that'll be just whatever it originally was set at. And finally, the only thing we have to do to make the AI actually go in that direction is just set our desired velocity equal to the waypoint position minus the global position normalized multiplied by the maximum velocity. That's pretty much it. That'll make the limb controller go ahead and be pushing in the correct direction all the time. Now, there is some adjustments we need to do specifically involved with the grounded state so that the AI knows how to jump to attempt to reach the target locations. But this is pretty much it for the basic enemy navigation agent. I'm going to go ahead and create a little debug active here, and this is just going to take and build a line from the current position towards the next waypoint position that is the color green with a lifetime of delta multiplied by 2. That way there's always just kind of a green line pointed in the next waypoint's direction based off of wherever the AI currently is. And that's just if the debug active equals true. And that's going to be it for this week. This one's a bit of a code heavy subject. I knew that it was going to be, that's why I kind of put it off until now. But the next video will hopefully wrap this up, get the AI actually moving around properly in order to work with this code. But this should handle the actual generation of the paths. So next week we'll be jumping in with the AI controller, making it work with this. As always, thank you all for watching. I hope you all have a wonderful week. We'll see you all back here next week for the next part of this tutorial.